Hi everyone, Mrs. Pasega here, and today we're studying for the Unit 2 test. So remember, for this review packet, I want you to try all the problems first. Don't just watch this video, copy it down, and think you're learning something. That's you following along, not you building the pathways you're going to need in your brain in order to remember and get functionality in how to use these skills. So if you look at the front of the review packet, you'll notice it has vocabulary, objectives, and it has this handy checklist. The objectives checklist is actually a list of all the types of problems I plan to ask you. And if you count them up, there's about, 20 or so objectives, and you're going to be getting like 29 questions on your test. So I'm going to ask in some question for you to describe the relationship between velocity and acceleration. When velocity changes, then you get acceleration. Go through this list and check off a few of the things that you feel like you know really well. Then make a plan to study the things you still struggle at. On the back, these mathematical relationships are the ones on your equation sheet for the most part. So let's get started. Chris and Pat are racing to see who can race the farthest in 20 seconds. Chris accelerates at 2 meters per second, which means that for every second of time that passes by, his velocity is going to increase by 2. He does this up until a top speed of 8. So that's 2, 4, 6, 8. Think of this as he's going faster and faster and faster and faster, but then he's going to go at constant speed for the remainder of this time. After that, it's 8s all the way down, and maybe you just want to just do that so we don't have to write 8 a billion times. So Chris is this shape right here. He accelerates at 2 meters per second squared for 4 seconds to reach a maximum velocity of 8. Pat then accelerates at 1 meter per second squared. So that means for every 1 second of time that passes, Pat goes faster and faster and faster. They increase at a rate of 1 meter per second squared up into 12 meters per second. So if we're doing this at 1 second, they're going 1 meter per second. At 2 seconds, they're going 2. At 3 seconds, they're going 3. And maybe we skip right up here to 12 so we don't have to do all the dots. They're going to go faster and faster and faster all the way up to 12 meters per second, and then go constant. This is a velocity versus time graphs. And on velocity versus time graphs, slope is represented by acceleration. To calculate displacement, we do area under the curve. And for velocity, you just read them off the y-axis, right? So if I asked you, what is Pat's velocity at 5 seconds? You'd be like, all right, at 5 seconds, Pat is going 5 meters per second. On a velocity graph, y-axis tells you the velocity. So you're just going to read the graph. The area under the curve of this graph represents displacement. And if you think of it like this, we're multiplying when we do displacement and area. We're multiplying a base in seconds times a height in meters per second. That means when the units cancel out, this area is actually in meters. So which one travels farther, you're going to calculate using the area under the curve. So when I go do this 8 seconds, which is traveling faster, they're actually traveling the same speed, assuming I drew my graph correctly. At 8 seconds, they're both going 8 meters per second. But who has gone farther? Then we have to do area under the curve. When I do area under the curve for up to 8 seconds, keep in mind I'm only shading. So at 8 seconds, whoever has traveled farther is the person who has the bigger area under the curve. So let me ask you this. What's the bigger area? This triangle? That's for Pat? Or this trapezoid for Chris? I got Chris's area is larger. Chris has traveled farther because area under the curve is how we calculate displacement. I actually don't have to do any math for this because I can visually see which area is greater. To me, this makes sense because Chris was accelerating faster. So at the beginning of the race, Chris traveled this much farther distance, like look at this little funky triangle area, traveled this much farther distance because he accelerated faster and went farther. But by the end of the race, that's a little trickier because by the end of the race, I'm eyeballing, are these two trapezoids the same area? This big one right here, big trapezoid, and this trapezoid. And that's hard to tell. I can't just eyeball this. I want us to calculate this. So I'm going to draw like little mini versions of each shape so you can kind of see what we're working with here. Chris has run a distance that's equal to this trapezoid. It's got a triangle up front with a base of 4 and a height of 8. Then the bottom of this rectangle goes from 8 to 20 seconds. That would be 12. So when I go calculate the area under the curve for Chris, this is going to represent displacement. We calculate displacement using area under the curve. So I'm going to add up the triangle, that's 1/2 base height, plus the rectangle, that's base times height. And if you ever forget these are on your equation sheet. So the triangle has a base of 4 and a height of 8. The rectangle has a base of 12 and a height of 8. Doing this out, Chris traveled 112 meters total. So now I'm just going to repeat the same thing for Pat. Pat had a much shallower slope at the beginning of theirs, but with a higher constant velocity at the end. Pat's can get broken up into a triangle with a base of 12 and a height of 12. Then this rectangle has a base of 20 minus 12, so it has a base of 8 and a height of 12, to be a total distance of 168 meters. So I had Pat traveling the farther distance, right? Because Pat went a larger area under the curve. Finally, we have G. Now, remember there's more than one way to calculate net force. If you knew like the applied force forward or backward or friction force, you could just subtract to get net force. But there is an equation on your equation sheet that you can use for this. We know the acceleration and the mass. Together, we have one missing number here. So substituting a 2 in for A and a 70 in for kilograms, we can solve for net force would be 140 newtons. Next, we have a high diver. The dot diagram is going to show free fall, which means the diver goes farther and farther every second, going faster and faster. In free fall, objects start slow, so the dots are close together, and end fast right before they hit the water. Free fall means that gravity is the only force acting on an object. So I don't want to see any drag or air resistance or applied force or normal force. Once they're in the air, and look for keyword free fall, then they're going to fall with just gravity to cause acceleration. Now, this is the height to, or the time to fall 20 meters. So xi is 20 meters. That's where you start. And down at the water, like assuming this is water down here, xf equals 0. Remember, x's are position. So we're starting with a position of 20 and ending on the ground for 0. We can assume in this case our diver is starting from rest and that their acceleration is negative 9.8 meters per second squared. Because they're in free fall, we automatically know what the acceleration is. It asks you to calculate the time and the final velocity. So let's do time first because it was listed first. On your yellow equation sheet, if you pick the equation from kinematics that has time in it but not VF, you're going to find this one. How you pick an equation is pick the equation that has t but not VF because you don't know it. Substituting in, I have 0 equals 20 plus 0 t plus 1/2 negative 9.8 t squared. I can simplify some of this out. 0 equals 20. This is plus 0, so that's nothing. And 1/2 of negative 9.8 is 4.9. To get t by itself, I'm going to subtract 20 to the left. Remember, if you're solving something where the algebraic expression already has the symbol you're looking for in it, you do the order of operations backwards. So I'm going to subtract first, then divide. So dividing by 4.9 on both sides, I get something like 4.01 is equal to t squared. That's math I can functionally do in my head. Taking the square root of both sides, t is 2 seconds. Once you find that t is 2, which makes sense. If you've ever watched a diver, they don't take that long to hit the ground or pool, right? Once we find that time, any of the other kinematics equations will work to find VF. So I'm going to choose the easiest one because that's how I want to be, right? VF is equal to 0 minus 9.8 times 2. Now I do order of operations forward because the equation I'm looking for, or the value I'm looking for, is already by itself in the numerator. So negative 9.8 times 2 is negative 19.6 meters per second. That makes sense for me because as this person falls, they should get faster and faster and faster in the negative direction. They're traveling down. So this is supposed to be a velocity versus time graph. And if this were a student, they would lose points for their labeling. So put velocity on one axis, put time on the other axis, add some units here. This diver starts from rest, so that's 0, 0. And at 2 seconds, they're going negative 19 meters per second. So using these two numbers, we know this data point at 2 seconds, negative 19.6, and this data point, 0, 0. Connect that all up. Sorry, my line's not super straight. If the diver were half as massive, that would not change their acceleration. The acceleration due to gravity is the same for all objects. Do you remember how acceleration is caused by a net force acting on a mass? Well, if gravity is their only force, then weight is pulling down, making them speed up, but mass has inertia, making them slow down. The masses cancel out when gravity is the only force. So no matter what the mass does, acceleration is equal to negative 9.8 for all masses. The caveat or special thing to keep in mind here is that that only works if gravity is the only force. If this is a fan cart, you're pushing on it, something like that, m's don't cancel out, and then you don't get 9.8. Like, it wouldn't make sense to have the free fall acceleration of negative 9.8 when the thing that's doing the pushing is a fan cart. Now, if there was air resistance, the motion of the diver would definitely change. That would decrease the net force because, like, the gravity would be pulling down and drag would be pulling up. It would mean it would take longer to fall because instead of going really quickly, air resistance would slow you down. When air resistance acts in opposition to gravity, it's going to mean there's less net force, which makes acceleration lower, which means it will take longer to reach the ground. G is asking about the 5 S's of air resistance. So Eric is looking to do a practice jump from a height of 20 meters, and he wants to take it slow. To make air resistance smaller, we need to think about the 5 S's. That's size, shape, surface area, surface material, and I'm going to leave speed off because he says he wants to go slow, so he knows speed is already a part of this. So if we want to increase the force of air resistance, we want to have a bigger size. That might mean that he's gonna try and put his body flat down, so it makes the big surface area. For shape, he can move his body into a shape that has more air resistance. Think of it like a pencil dive. When you're just going straight up and down, like whoop, would have very low air resistance. But if you were doing all sorts of like twists and turns and like spreading your body out, your shape could make you have more air resistance. Now, a very silly thing, surface material. He could cover himself with a surface material that has that has more air resistance. Like, I guess you could put a bunch of feathers on and that would make more air resistance, right? But think of the S's. So size, shape, surface area, surface material, and we already know he wants to slow down the speed. Finally, on this page, a graph that shows positive acceleration that is slowing down is actually going to look something like this. How do I know they have positive acceleration? It's got a positive slope. How do I know it's slowing down? Well, if you started with a speed of negative 18 meters per second and you went to 0, then your speed is getting closer and closer to 0. And that's not a contradiction. That's because a negative acceleration and a positive velocity are going to slow down. Whenever acceleration and velocity are pointed in opposite directions of each other, then you get slowing down. So notice our free fall due to gravity, that's actually speeding up, even though acceleration was negative. The velocity is negative, and the acceleration is negative. So when they match, they speed up. Now, I do expect you to have some lab-based questions in your test. So let's say we do a lab that's very similar to the one we did for friction. In this one, we have the sample material that's for shelving. We've got a mass of the shelving material and the mass of the block. When they're being pulled at constant speed, that means equilibrium. Dynamic equilibrium, to be precise, right? That means the normal force up equals the gravity or weight pulling down. That means the applied force from the spring scale to the right, so let's put that as Fs to the right, is equal to friction to the left. And when we do this experiment, we get a graph that looks like this. The static region is right here. This is when you're pulling, but it hasn't started moving yet. The threshold of motion is up here, that like maximum of the static friction section. And the kinetic section is once you've like push, it starts moving and then it slides. From the graph, I can read FFS. The threshold of motion is where like the static force is a maximum. And that looks like about 5.5 newtons, like estimating this from the graph. FFK, it's giving you the mean right there, is 4.44 newtons. FG, oh, I'm making you do review stuff. FG is weight, where I'm going to take the 0.7 kilograms total and multiply it by 9.8 to get the weight in newtons. Now, if I was filling out this free body diagram, I would see that the 6.86 newtons that pulls down is going to be equal to 6.86 newtons that pull up. Those have to be equal because we know it's an equilibrium. When I've highlighted and underlined or like bolded words like constant speed, that's for a reason, because I want you to see that the forces are canceling out. It's in equilibrium from unit 1. Now, ultimately, what this employer has to do is minimize friction. We're going to try and calculate these coefficients of friction so they can figure out how to make those smaller. So to calculate coefficient of friction, we're going to do this once for static and once for kinetic. And the only difference in here is one time where you're going to use the static friction force. So for static, I'm going to use 5.5. But I'm going to use the same normal force for both. For kinetic, I'm going to use 4.44. But I'm still going to use a normal force of 6.86. Dividing on both sides to get mu by itself, I get a coefficient of friction of 0.8 for static and 0.65 for kinetic. Notice that kinetic should always be less than static. Now, E is kind of a trick question, but what it's getting at is trying to make you understand what coefficient of friction is. Coefficient of friction is the material value for this shelving material plus cardboard. So if I pile more weights on top, does it change the material? No. If I fold the cardboard in half and make the surface area small, is it still cardboard? Yep. So mu doesn't change because the material hasn't changed. Using a rougher material would do. That would increase mu, but the weight wouldn't change it at all. So in order to minimize friction, the things you can do are try to lower the two things that impact friction. Lower the coefficient and lower the normal force. You can lower the coefficient by using a smoother material, or you can make the normal force smaller by changing the mass. Putting less mass on would make it easier to move because friction would be smaller. Number 4 is a lot about motion. Self-driving cars going in this problem, and we want to figure out how far it's traveling and the time it takes to come to rest. We know that it starts at 15 meters per second, so I'm going to put that in for VI. We know that it's going to stop at the end because it's coming to rest. And I know that it starts at the beginning. So XI is almost always 0. And its acceleration is -3. Because the kinematics equations, only 2 of them are unique, that's what I'm looking for before I start a kinematics problem. I want to see 2 unknowns because I only can use 2 equations. Since it says time first, I'm going to pick an equation that has t, but not xf, which luckily is the easiest equation. So putting in vf of 0, vi of 15, and we're solving for t. This is one of the ones where you don't do order of operations in PEMDAS order. You're not going to start with like the parentheses and stuff. You're going to start with addition and subtraction. So I'm going to subtract 15 to the left. Next up, we're doing division, dividing by -3 to the left. This means t is equal to -15 over -3. And don't put this in your calculator. What's 15 divided by 3, guys? It's 5. And finally, once you figured out that t is 5, either of the other 2 equations can be used to calculate distance. So I'm going to go with this one because this one's already set to calculate distance. It has distance by itself on the left already. That makes my life easy. So initial velocity is 15, time is 5. Acceleration is -3, and the time is 5. I get a distance of 37.5 meters. Since this is something that has a positive velocity to start and is slowing down, I'm looking for this position graph with a negative acceleration. So which one of these has that smiley face? Yeah, that's B. B is the one that shows negative acceleration. So notice the velocities are positive because these slopes are positive. But the acceleration is negative because it's that downward facing curve. The velocity graph, on the other hand, has to show that it starts fast at 15 and goes slow, goes down to rest. So I also had B for the velocity graph. As a dot diagram, this is something that's going fast to start and going slower, so traveling less and less and less distance every second. A dot diagram shows big spacing when it's fast and small spacing when it's slow. So this is an object that's not in equilibrium. And this cannot be in equilibrium because equilibrium means constant velocity. This means there's some sort of unbalanced force thing going on. And of course there is. This would be an object where friction from the brakes is bringing our object to rest. So finally, for F. Like I said earlier, you can calculate net force by subtracting if you knew the applied force and the friction force. But remember, the other way to calculate net force is like this, right? The acceleration is -3. The mass of this car is 1,000. To get F net by itself, I'm going to multiply 1,000 to the left. So I have a net force negative 3,000 newtons. So hey, here's another lab one. In this lab, this group kept mass the same the whole time. That must be the control variable, mass. And they changed the force and measured acceleration. At this point, you should know that force causes a change in acceleration, even if you didn't know which one they were working with. Like, even if they put these in the wrong order, force causes acceleration to change, so force must be the independent variable. This is probably something where like they're pushing harder and harder and harder and measuring the resulting acceleration. So I said that I would disagree with B because this student says like the purpose is to experience the relationship between mass and acceleration, but it's not. Mass was kept the same the whole time. They were actually investigating force versus acceleration. And when the student wrote that the data showed there was no relationship between applied force and acceleration, I would disagree. This clearly shows a direct relationship. And you can kind of like eyeball the graph in your head, right? This is a relationship, whereas the force doubles, going from 10 to 20, the acceleration doubles, going from like 1.4 to 2.9. Them choosing to go up by force in tens each time isn't a conclusion. That's a procedure. So in this, I would note that as force increases, acceleration increases. The graph would look something like graph A. So this student is incorrect. There is a direct relationship because as force increases, acceleration increases. The other word for this would be proportional. And finally, mass versus acceleration. That's graph D. That's why I had us look at everybody's posters, even though our labs could have been like a little overlapping. Graph D shows us that as mass increases, acceleration is decreasing. And think of it like this: more massive objects have more inertia. That makes them harder to move or change their acceleration. So this acceleration should be getting closer and closer to zero. Notice this like asymptote here. And notice that it won't go into the negatives either, right? You can't have a negative mass on this side. So an inverse graph has like an asymptote on the y-axis and the x-axis, which ends us where we started this unit. We started this unit talking about inclined planes, specifically for our handicapped students that are going to need to be accessing our building and our spaces. Let's talk about the inclined planes at the Olympics then. We've got our athlete that's going down this really big 30-degree incline, and we know that gravity is pulling them down. We know gravity is always going to pull down. And normal force is going to be perpendicular to the angle of our ramp. So if that's our ramp right there, normal force is going to go up and to the right. And notice when you're drawing these that normal force should be smaller than gravity force. Now, the modified free body diagram is going to look really, really similar. So let's draw our ramp in. Let's draw our normal force in. But the modified free body diagram is going to replace FG with its parallel and perpendicular components. Remember, FGY is the component that cancels out normal force. Think of it as like it's a portion of the gravity force. FGX is how much is left over to cause acceleration going down the hill. FGX's job is to cause acceleration, and FGY's job is to cancel normal force. So when we go calculate the weight of the sled, This, every time I say calculate weight, you should be pulling out this Fg equals mg. You do have to remember stuff from previous units, guys. So I put in an 80 kilograms for the mass times 9.8 for g to get 784 newtons down. So think of this Fg as that's the total force. So Fg should be bigger than either of its two components. The Fgx and Fgy components are right on your equation sheet. Fgx is going to be mg sine theta, and Fgy should be mg cos theta. So sometimes people are asking me, like, how do I know which one is which? That's why it helps to do these sorts of practices where we see, like, oh, Fgy is the one that cancels normal force, and Fgx is the one that causes acceleration. Because when it asks for components, it's only these two equations. So for m, let's put in 80 kilograms for m. M is mass and measured in kilograms. G is 9.8 on Earth. And we're going to put in the ramp angle of 30 degrees. Actually, in for both of them, these two substitutions should look very similar to each other, except one is sine and one is cosine. So let's get these into our calculator and show you a thing that might happen. When you do sine and cosine in Desmos or on a regular calculator, sometimes you'll get a thing where it automatically calculates it in radians. Like, does negative 700 something make sense? No, Fgx should always be a positive number. So hit this little toolbar button, change it from radians to degrees, because it was 30 degrees for our ramp, and that will give our answer. So there's 392 newtons in the x direction, pulling you downhill. This is the force that wants you to speed up. And like 679 newtons in the y direction. So which one of these two forces is going to be equal to the normal force? Hint, it's on the screen. Fgy is the force that's going to cancel the normal force. So when it says calculate normal force, you actually don't have to. This force is the one that cancels Fgy. So in fact, let's just double check. Is my normal force smaller than my weight? Yes, I have done this correctly. And I don't have a negative number, which makes sense because I can't have a negative normal force. All right, so now let's get acceleration. This acceleration is caused by a net force acting on a mass. Which force causes acceleration? Is Fgx. Fgx is the only force that doesn't cancel in this picture, right? Normal's not causing acceleration. Fgy is not causing acceleration. Fgx is. So that's why you're putting it in for net force. Remember that this mass is 80 kilograms. Mass in kilograms, not in newtons. And finally, dividing this out, I get 4.9 meters per second squared. And the direction for this is downhill. Now, let's say our ramp is getting a higher and higher and higher angle. Does that change the weight? No. The weight stays the same, because remember, weight is calculated by just mg. So as angle goes up, the weight stays the same. Think of this as weight as your total gravitational force. And the total gravitational force is just mg. This is going to stay the like 784 newtons. As angle increases, the normal force goes to 0. the normal force gets smaller and smaller and smaller. And if you remember, a cosine function starts big and goes to 0. Normal force, Fn, goes like mg cosine theta because it goes along with fg y. And here's something you got already. As the angle gets bigger, you know that the acceleration should get faster and faster and faster. Fgx increases, making the acceleration increase. So Fgx gets bigger, causing faster acceleration. Fgy gets smaller, causing a smaller and smaller normal force. All right, folks. Well, best of luck on your test. See you soon.